So thus far we've been talking about bonds between atoms that make up molecules or compounds. Now I want to talk about forces between molecules. So these are forces that are much less strong than an actual molecular bond, but they are important. And the first one is called hydrogen bond, which is a misnomer. It is not a bond. It's an attraction. And it means it occurs between hydrogens bonded to oxygen, fluorine, and nitrogen. So the most common time you see this is with water. Water can hydrogen bond. So we've got one water molecule, and here is its neighboring water molecule. We'll put neighbor in a different color. We get an attraction between this partially positive hydrogen and this partially negative oxygen. So, and usually people draw it as a dot. So that is a hydrogen bond, or hydrogen attraction, and it's one of the strongest of our intermolecular attractions we'll be talking about. The next one is a dipole-dipole interaction. These attractions occur between the positive bit on one molecule and the negative bit on another. So this is an attraction between partial positive and negative charges. The last one and the weakest are dispersion forces. These are sometimes called London forces. These are attractions between nonpolar molecules. And they're caused by temporary dipoles that form randomly. Attractions between nonpolar. Okay, so we want to look at molecules and identify the strongest attraction between the particles. We'll start with methanol. Well, immediately we should see that we have a hydrogen attached to an oxygen. So we have hydrogen bonding. And that's one of the strongest ones that I'll be talking about. Only one stronger would be an ionic bond, and we'll see that in a minute. Okay, here's carbon monoxide. Well, carbon monoxide is a carbon bound to oxygen. We've got, this is going to be a polar bond. The dipole is going to be, carbon is going to be partially positive and oxygen will be partially negative. So we have a dipole. That means that we'll have a dipole-dipole interaction. So this one will be a little bit attracted to the next one. And so forth down the line in solution. Then let's look at carbon tetrafluoride. If we look at the electronegativity for the carbon and the fluorine, carbon is 2.5, fluorine is 4. So we've got a difference here of 1.5. The difference in these numbers. Okay, so that means that we have polar covalent bonds. But let's do our Lewis structure and see what the structure of this compound looks like. Let's see, we've got a carbon in the middle, and we're going to put the fluorines on the outside. Carbon gives us 4 electrons, and each of the 4 fluorines gives us 7. That's 32 electrons. We use up 8 of those in our bonds. 2, 4, 6, 8 go to bonding the molecule together. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so there's our structure. If we look at the form of it, it has a central atom, and it's got 4 bonded atoms. That means that we have tetrahedral. Since it's symmetrical, there are 4 fluorines, this will be nonpolar. But wait a minute, the bonds were polar. That doesn't matter. As long as the structure is a tetrahedral and it's symmetrical, it'll be nonpolar because all those polar bonds are just going to cancel out. So let's skip down and identify the major attractive force between these. So we've got a bromine and a fluorine. Again, we need our electronegativity table. You've got bromine at 2.8, fluorine at 4. So we've got 4 minus 2.8, and that's going to be equal to 1.2, and that means you've got a dipole. You've got a polar bond. There's a polar bond, and you're going to have a dipole. Dipole interaction. If we look at potassium chloride, we see that we've got chlorine at 3 and potassium at 8. That gives us a difference of 2.2. That's going to be an ionic bond because it's greater than 1.8. And so we'll have ionic interactions. Those are even stronger than the hydrogen bonding. So here we have our last question. It's asking us to identify the substance in each of the following pairs that would have the highest boiling point. Well, if you have strong attractions between your molecules, it's going to be difficult or require more energy for it to boil. So strong attractions mean higher boiling point. I've listed the attractions here in order. Ionic attractions are the strongest. Hydrogen bonding is next. Remember, you need a hydrogen that's attached to a oxygen, fluorine, or nitrogen for that. Dipole-dipole is any time that you've got a dipole moment for your molecule. And dispersion, which are London forces, which are nonpolar molecules. And they're the very weakest. So first we're going to compare sodium chloride and hydrochloric acid. If we are looking at these, sodium is 0.9 and chlorine is 3. So we've got a difference of electronegativity of 2.1. That makes this compound ionic because it's got that big electronegativity difference. Hydrogen and chlorine has a difference of 0.9. We would expect it to be a covalent bond. It'd be polar covalent, but it'd still be covalent. So sodium chloride is going to have the higher boiling point because it's ionic, and ionic beats covalent bonds. Hydrogen fluoride or hydrogen bromide? Well, hydrogen fluoride is going to have a difference It's going to have hydrogen bonding because it's a hydrogen attached to fluoride. So this one hydrogen bonds. That's going to give it the highest boiling point. This one is going to be polar covalent. And this one is ionic, so it's going to have the higher boiling point. The last one here, this one can hydrogen bond, and that gives it the higher boiling point.